Hello, friend. Some nights, when the world quiets down and the sky opens wide, you might look up and wonder about the dance happening above. The planets spinning in their orbits, the moon tracing its path, everything moving, turning, flowing in one direction, like a cosmic river that never stops. But why? Why does everything in our solar system move the same way? Why don't planets wander in chaos, spinning backward, crossing paths, colliding in the dark? What invisible hand guided them all into this elegant, synchronized motion? Tonight, we'll drift into that question, not to solve it quickly, but to let it unfold gently the way the universe itself once did, slowly, quietly, over billions of years. Before we begin, if you find comfort in these quiet journeys through space and time, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Tonight, we're not just asking why planets move in the same direction. We're asking something deeper. Why does anything in the universe have order at all? Why isn't everything just scattered, random, lost in the void? The answer begins long before there were planets, long before there was a sun. It begins in a time when our corner of space was nothing but darkness cold, and a vast cloud of gas and dust floating silently through the galaxy. You don't need to understand everything right away. Just rest and let curiosity do the listening. Picture this: 4.5 billion years ago, where our solar system now exists, there was only emptiness. Not the kind of emptiness you imagine when you think of space already filled with stars and galaxies. This was a quieter emptiness, a pocket of the Milky Way that hadn't yet awakened. But it wasn't truly empty. If you could have floated there billions of years ago, you would have found yourself inside something vast and invisible. A cloud, not made of water vapor like the clouds we see on Earth, but of hydrogen and helium, the simplest, most ancient elements in the universe. Mixed within that gas were tiny grains of dust, particles so small you'd need a microscope to see them, bits of carbon silicon iron, remnants of stars that had lived and died long before. Scientists call this a molecular cloud. Some call it a stellar nursery. But perhaps the most poetic name is the one that stuck a nebula, from the Latin word for mist. This cloud was enormous. If you tried to measure it, you'd find it stretched across trillions of kilometers. To cross it, even at the speed of light, would take years. Its mass was staggering, perhaps 1,000 times the mass of our sun today, maybe more. And yet, despite its size, it was thin, fragile, the kind of structure that seems too delicate to birth anything solid. But within that fragility was potential. The cloud wasn't perfectly still. Nothing in the universe ever is. It drifted through space, carried by the slow currents of the galaxy. And as it drifted, small things began to happen. A wisp of gas here nudged by a distant star's light. A clump of dust there pulled slightly by gravity. These were tiny events, insignificant on their own. But the universe is patient. Over thousands, perhaps millions of years, the cloud began to shift. Not in any dramatic way. There were no explosions, no sudden changes. Just a slow gathering, a gentle pulling inward, as if the cloud itself was learning to breathe. Gravity, you see, doesn't rest. It's always there, always pulling, always patient. And in this cloud, gravity began to notice itself. The denser parts of the cloud where gas and dust had clumped together started pulling on the less dense parts. Slowly, almost imperceptibly, the cloud began to contract. Scientists suggest this process might have been triggered by something external. Perhaps a nearby star exploded in a supernova, a violent death that sent shock waves rippling through space. When those shock waves hit our quiet cloud, they compressed it, squeezed it, gave it the nudge it needed to begin collapsing. Or perhaps it was something gentler. A passing star, its gravity tugging on the cloud as it drifted by. Or maybe just the natural turbulence of the galaxy itself, eddies and currents in the vast ocean of space, disturbing the stillness. We don't know for certain which event started it, but we know this. Once it began, there was no stopping it. As the cloud contracted, something remarkable happened. It started to spin. Now, you might wonder, why would a collapsing cloud start spinning? Why wouldn't it just fall straight inward, like water down a drain? The answer lies in something called angular momentum. It's one of the fundamental laws of the universe, as unchanging as gravity itself. And it's the reason everything in our solar system moves the same way today. Here's how it works. Imagine you're on a playground, standing near a merry-go-round. You give it a gentle push. It starts to turn slowly at first. Now imagine you hop on and pull your arms in close to your body. Suddenly, you're spinning faster. You didn't add any energy, you just changed your shape. That's conservation of angular momentum. The same thing happens in space. Our primordial cloud wasn't perfectly still to begin with. It had tiny motions, microscopic swirls and eddies, invisible currents of gas drifting this way and that. These motions came from the cloud's birth, from the turbulence of the galaxy, from ancient disturbances long forgotten. When the cloud began to collapse, those tiny motions didn't disappear. They couldn't. The universe doesn't allow that. Instead, as the cloud got smaller, those motions intensified. The cloud began to spin faster and faster, like a figure skater pulling in their arms. And here's the crucial part, because the cloud was already spinning. Even just a little, it couldn't collapse into a perfect sphere. Instead, it flattened. It spread out into a disk, like pizza dough, spun in the air, or like water swirling down a drain. This is called a protoplanetary disk, and it's where our story truly begins. Within this spinning disk, everything moved in the same direction. Not because something told it to, not because there was a plan, but because the original cloud had been spinning that way from the start. Every particle of gas, every grain of dust inherited that motion. They had no choice. The direction of spin, counterclockwise if you looked down from above the disk's north pole, was baked into the fabric of the cloud from the very beginning. This is why today all the planets orbit the sun in the same direction. They're still following the motion of that ancient cloud, spinning the same way it did 4.5 billion years ago. It's a kind of memory, a cosmic memory written not in words or images, but in motion itself. Think about that for a moment. Right now, as you listen to these words, Earth is moving through space at about 30 kilometers every second. It's tracing an elliptical path around the sun, completing one full orbit every 365 days. And it's doing this in the same direction that Jupiter orbits, that Mars orbits, that Saturn and Neptune and all the rest orbit, not because they're following each other, but because they're all following something much older. An echo of motion from a cloud that no longer exists. Some people imagine the solar system as something designed, something placed carefully by a cosmic architect. And in a way, it is designed, but not by intention. It's designed by physics, by the simple, elegant laws that govern matter and motion. If that cloud had been spinning the other way, our planets would orbit the other way. If it had been spinning faster, our solar system might look very different, perhaps larger or more chaotic. If it hadn't been spinning at all, which in reality is nearly impossible, then perhaps no planets would have formed at all. But it was spinning. Just enough. Just right. And from that spin, everything followed. Here's a question worth pondering, though. Was our cloud special? Or is this how all solar systems begin? The answer, it seems, is the latter. When astronomers look out into the universe with powerful telescopes, they see other clouds like ours. Vast, dark nebulae slowly collapsing under their own gravity. And in many of them, they see disks forming. Spinning disks of gas and dust glowing faintly in infrared light. These are other solar systems being born right now in real time. And they're all spinning. All of them. Because the same laws that shaped our solar system are shaping theirs. One of the most famous images ever captured is of a star system called HL Tauri. It's about 450 light-years away from us in the constellation Taurus. When astronomers pointed the ALMA telescope at it, they saw something breathtaking, a young star surrounded by a perfectly flat disk of gas and dust. And within that disk, they saw gaps, dark rings where planets were forming, sweeping up material as they grew. The disk was spinning, all in one direction. Just like ours once did. It's humbling in a way to realize that what happened here wasn't unique. That the motion we see in our night sky, the planets drifting across the ecliptic, the moon rising and setting, is part of a pattern that repeats across the galaxy, perhaps across the universe. We are not at the center of anything, but we are part of something vast. Something ancient, something that began long before we existed and will continue long after we're gone. Before we move on, let's pause on one more thought. When you look up at the night sky and see a planet Venus glowing softly in the evening, Jupiter bright and steady, you're not just seeing an object in space, you're seeing motion made visible. You're seeing the memory of a cloud that collapsed 4.5 billion years ago, still expressing itself, still moving, still spinning. And you're part of that motion too. Earth carries you with it around the sun through space at speeds so fast they're almost unimaginable. 30 kilometers every second, and yet you feel nothing. Because you've been moving that way your entire life. Because everything around you moves the same way. We are all passengers on a spinning disk inherited from a cloud that no longer exists. Isn't that something? The story doesn't end with the cloud beginning to spin. That was just the first breath. What happened next, how that spinning disk gave birth to a star, to planets, to everything we see today, is a story of collapse of heat, of collisions in the dark. And it's where we'll drift next, as we watch the cloud pull itself inward, faster and faster, until something new begins to glow at its center. So, the cloud began to spin. But spinning wasn't enough. Something else had to happen. Something that would transform a formless mist into a structured system, a place where planets could someday form. that something was chaos. Not the chaos of destruction, but the chaos of possibility. The kind of disorder that holds within it the seeds of order. Because before there was elegance, before there was the graceful dance of planets, we see today there was turbulence. There was violence, quiet and slow, but violence nonetheless. Let's go deeper into that cloud. Let's see what it was really made of and why it had to be exactly the way it was 4.6 billion years ago, give or take a few million years, which in cosmic time is barely a blink. Our solar nebula was not a single uniform thing. It wasn't like a smooth fog rolling across a valley. It was lumpy, inconsistent, full of variations that would seem random if you didn't know what to look for. Imagine standing inside it, if such a thing were possible. Around you, darkness. Not complete darkness. There would be faint starlight filtering through from distant suns, perhaps a subtle glow from the Milky Way itself. But mostly, you'd be surrounded by cold and silence. The temperature here was brutal. Scientists estimated hovered around negative 260 degrees Celsius. That's close to absolute zero, the coldest temperature theoretically possible. At that temperature, most gases freeze solid. Water becomes ice harder than steel. Carbon dioxide becomes dry ice that could shatter if struck. And yet, the cloud remained gaseous because it was made mostly of hydrogen and helium elements, so light, so resistant to freezing, that even in this frigid void, they stayed in their gaseous form. These two elements alone made up about 98% of the cloud's mass. Hydrogen, the simplest atom in existence, formed when the universe itself was born. Helium forged in the first few minutes after the Big Bang. Everything else, the remaining 2%, was what astronomers call metals. Not metals in the everyday sense like iron or copper, though those were there too. In astronomy, a metal is anything heavier than helium. Carbon, oxygen, nitrogen, silicon, magnesium, iron, gold, uranium, every element on the periodic table beyond the first two. These heavier elements weren't born in the Big Bang. They were created inside stars, forged in nuclear furnaces over millions or billions of years, then scattered into space when those stars died. Some went quietly, puffing off their outer layers like dandelion seeds on the wind. Others went violently exploding as supernovae blasting their guts across light years. Our cloud contained the ashes of those ancient stars, remnants of deaths that happened long before the sun existed. And within those ashes were the ingredients for everything solid we know today. Every planet, every moon, every grain of sand, every atom in your body. You are made of stardust, not poetically, literally. The dust grains floating in that cloud were microscopic. Most were smaller than a single micron, about 1/70th the width of a human hair. You'd need a powerful microscope to see them individually. And yet, there were countless trillions of them, suspended in the gas, like motes in a sunbeam. These grains weren't smooth. Under magnification, they looked jagged, irregular, tiny fragments of minerals and frozen gases. Some were made of silicates, similar to sand on Earth. Others were carbon-based, like graphite or soot. Some were metallic iron, nickel, magnesium. And coating many of them was a thin layer of ice. Not just water ice, but also frozen ammonia, methane carbon monoxide. These grains were survivors. They had been through stellar winds, supernova shock waves, the harsh radiation of open space. And now, they drifted slowly, tumbling through the cold, waiting for gravity to bring them together. But here's something most people don't realize: the cloud wasn't static. It wasn't just sitting there waiting patiently to collapse. It was turbulent, active, restless. Within the cloud, there were currents, flows of gas moving at different speeds in different directions. Some regions were denser than others. Some were warmer. Some were ionized, stripped of electrons by radiation from nearby stars. The cloud was a patchwork of conditions, a three-dimensional landscape of invisible complexity. And it was loud, not loud in a way you could hear, of course. Sound can't travel through the vacuum of space. But if you could translate the motion of gas into sound, the cloud would have roared. Subsonic waves rippled through it, pressure disturbances moving at hundreds of meters per second. These waves were caused by all sorts of things: magnetic fields threading through the gas, twisting and snapping, shock waves from nearby stellar winds, turbulence from the cloud's own rotation. Scientists call this supersonic turbulence. It's one of the reasons clouds like this don't collapse smoothly. The turbulence fights against gravity, creating pockets of resistance, slowing the infall, making the process messy. But gravity is patient. And gravity always wins. As the cloud began to contract, something interesting happened to its shape. Remember, it was already spinning slowly at first, but spinning nonetheless. And as it contracted, that spin accelerated following the law of conservation of angular momentum we talked about earlier. But the cloud didn't contract evenly in all directions. Gravity pulled inward from all sides. Yes, but the spinning motion created an outward force along the equator, what we call centrifugal force. This force resisted the collapse in one direction, allowing the cloud to flatten. Think of it like this. If you take a blob of dough and spin, gravity pulls it into a sphere. But if you spin it fast enough, the centrifugal force pushes outward at the equator, and the dough flattens into a disk. The same thing happened to our cloud, just on a vastly larger scale and over a vastly longer time. The result was a structure called an accretion disk, a flat, rotating pancake of gas and dust with most of its mass concentrated toward the center. How big was this disk? Enormous. At its widest, it may have stretched across 200 astronomical units. One astronomical unit, abbreviated AU, is the distance from Earth to the Sun, about 150 million kilometers. So this disk was 200 times that distance across. If you placed the Sun at the center, the disk would extend far beyond the orbit of Pluto, out into the region we now call the Kuiper Belt. And yet, despite its size, it was thin. Relative to its width, the disk was almost paper thin, perhaps only a few astronomical units thick at most. A cosmic crepe. Within this disk, the density varied wildly. Near the center, where gravity's pull was strongest, gas and dust piled up. The pressure increased. Particles collided more frequently. This would become important. Later, this is where the Sun would be born. Farther out, the disk was thinner, colder. Here, the spacing between particles was vast. A dust grain might drift for years without hitting another. And yet even here collisions happened. Slowly, patiently. One grain sticking to another. Then another, building something larger. Grain by grain. But we're getting ahead of ourselves. One of the common misconceptions about this early stage is that the cloud was calm, serene, like a still pond. People imagine it as a peaceful place gently coming together under gravity's soft embrace. the reality was far more chaotic. The turbulence within the cloud created eddies and vortices spinning whirlpools of gas that could be larger than our entire solar system today. These vortices could last for thousands of years, trapping dust and gas, concentrating them in certain regions. Some scientists believe these vortices may have been the places where planets first began to form like seeds planted in fertile soil. There were also shock waves. Remember that the cloud's collapse may have been triggered by a supernova. Even after that initial trigger, shock waves continued to ripple through the gas echoes of violence, compressing and heating the material they passed through. These shocks created instabilities regions where density increased suddenly, where gravity could get a stronger foothold. And then there were magnetic fields. This part is often overlooked, but it's crucial. The gas in the cloud wasn't entirely neutral. Some of it was ionized atoms, stripped of electrons, creating charged particles. And charged particles interact with magnetic fields. The galaxy itself has a magnetic field, and our cloud was threaded with it, like iron filings aligned near a magnet. These magnetic fields did something remarkable. They linked different parts of the cloud together. Gas in one region could influence gas in another, even if they were light years apart. The fields also resisted the collapse in certain directions, adding yet another layer of complexity to the process. It's a bit like trying to compress a spring. You can push it down, but it pushes back. The magnetic fields added a kind of springiness to the cloud, making the collapse slower, more controlled. And perhaps that's a good thing, because if the cloud had collapsed too quickly, it might have formed a single massive star, a giant that would burn brightly and die young, never giving planets a chance to form. The turbulence and magnetic fields slowed things down just enough to allow structure to emerge. Let's talk about one more aspect of this primordial cloud, its composition. Because not all of the cloud was the same. Near the center, where temperatures would eventually rise as the collapse intensified, only the most heat-resistant materials could survive. Metals, silicates, rocky minerals. The ice's water, ammonia, methane would evaporate here, turning back into gas. But farther out, where it stayed cold, the ices remained solid. This created a natural divide in the disk, a line astronomers call the frost line or snow line. Inside this line, only rock and metal. Outside rock, metal, and ice. This line would determine what kinds of planets formed where. Close to the sun, small rocky planets like Earth and Mars. Far from the sun, giant planets with icy cores like Jupiter and Neptune. The frost line in our early solar nebula was probably around 3 to 5 astronomical units from the center, somewhere between the current orbits of Mars and Jupiter. That's not a coincidence. It's where the temperature dropped low enough for water to freeze, allowing much more material to accumulate. And here's something fascinating. We can see frost lines in other protoplanetary disks today. Using telescopes like ALMA, astronomers have observed young star systems and spotted these dividing lines, bright rings in the disk where ice suddenly appears. It's like seeing a photograph of our own past, frozen in time, 4.5 billion years ago. Have you ever wondered why the outer planets are so much larger than the inner ones? The frost line is part of the answer. Beyond it, there was simply more material available. Not just rock and metal, but also ice, which is abundant in space. More material meant more building blocks for planets to grow from. But we're not to planets yet. Not even close. At this stage, the disk was still mostly gas with a small percentage of dust. The dust grains were tiny, isolated, drifting. They hadn't begun to stick together in any meaningful way. Not yet. Let's pause for a moment and consider what this cloud represented. It was a place of pure potential. Every atom in it carried the possibility of becoming something else. A star, a planet, a moon, a comet, an asteroid. One day perhaps a molecule in a living cell. The universe doesn't plan. It doesn't design. It simply follows rules, laws of physics that play out across time. And yet from those simple rules, complexity emerges, structure emerges, beauty emerges. The chaos of the cloud wasn't random. It was necessary. Without the turbulence, without the variations in density and temperature, without the magnetic fields and shock waves, the collapse might have happened too uniformly. Everything might have fallen into the center and formed a single object. No disk, no planets, no us. Instead, the chaos allowed for diversity. It created the conditions where different outcomes were possible, where some material stayed near the center and some drifted outward, where some grains collided and stuck together while others remained solitary. Chaos, in this sense, is the mother of order. So there, it was a vast, spinning disk of gas and dust, turbulent and cold, threaded with magnetic fields rippling with shock waves. A place that looked like disorder, but held within it the blueprint for everything we see today. The cloud had been set in motion. It was spinning, collapsing, flattening, and at its center, something new was beginning to stir. A concentration of matter, growing denser and hotter with every passing millennium. A heartbeat, faint but steady, preparing to ignite. That's where we'll turn our attention next, to the birth of something that would change everything. The moment when the disk stopped being just a cloud and became a system. The moment when the sun began to wake. The cloud was collapsing, flattening, becoming something new. But there's a question we haven't fully answered yet. A question that sits at the very heart of why our planets all move in the same direction today. Why did the cloud spin at all? It seems almost too convenient, doesn't it? A massive cloud of gas and dust floating in space suddenly decides to rotate, as if it had intention, as if it knew what it was supposed to become. But the universe doesn't work on intention. It works on something far more elegant, the laws of motion. And one law in particular, conservation of angular momentum, is the invisible architect behind every spinning galaxy, every rotating star, every orbiting planet. Let's drift into that law gently and see how a cloud that seemed almost still could become a whirlpool that would spin for billions of years. Picture yourself standing in a vast, empty field at night. No light pollution, just you and the sky. Above you, the stars seem motionless, eternal. But that's an illusion. Everything in the universe is moving. The stars are moving. The galaxies are moving. Even the emptiness between them is expanding. Nothing is truly still. Our primordial cloud 4.5 billion years ago was no exception. It drifted through the Milky Way like a ghost carried along by the slow rotation of the galaxy itself. The entire galaxy spins once every 250 million years or so. Our cloud moved with it like a leaf floating on a river. But the cloud had its own motion too. Tiny, almost imperceptible movements within it. currents of gas flowing past each other, eddies forming and dissolving, random collisions between particles nudging them this way or that. These motions seem chaotic, insignificant. A few meters per second here, a few kilometers per hour there, barely noticeable across the vast scale of the cloud. But they weren't random. They couldn't be, because every motion in the universe carries with it a property called angular momentum. Angular momentum is, in simple terms, the measure of how much spin something has. It depends on three things: how much mass is moving, how fast it's moving, and how far it is from the center of rotation. And here's the crucial part. Once something has angular momentum, it can't lose it, not unless something else takes it away. This is the law of conservation of angular momentum. It's as fundamental as the conservation of energy. The universe doesn't allow angular momentum to simply disappear. So when our cloud began to collapse under its own gravity, all those tiny motions, all that angular momentum scattered throughout trillions of tons of gas and dust had to go somewhere. It couldn't vanish. It had to be conserved. And as the cloud shrank, something remarkable happened. The spin accelerated. Think of an ice skater performing a spin. She starts with her arms stretched out, rotating slowly. Then she pulls her arms in close to her body, and suddenly, she's spinning much faster. She didn't add any energy. She didn't push off anything. She simply changed her distribution of mass. When her arms were extended, her mass was spread out far from the axis of rotation. When she pulled them in, that same mass moved closer to the center. To conserve angular momentum, her rotation speed had to increase. The same physics applies to a collapsing cloud. As gravity pulled the cloud inward, the material moved closer to the center of rotation. And just like the ice skater, the rotation speed increased. This is why the cloud began to spin faster and faster as it collapsed. But where did that original spin come from? Why was the cloud rotating at all, even slowly, before it began to collapse? The answer lies in the universe's inherent messiness. When the cloud first formed, pulled together from the diffuse gas of the Milky Way, it wasn't perfectly symmetrical. The galaxy itself was turbulent, filled with stellar winds, supernova shock waves, magnetic fields, and gravitational tugs from passing stars. All of these created tiny asymmetries in the cloud's motion. Perhaps one side of the cloud was pulled slightly harder by a nearby star's gravity. Perhaps a shock wave from a distant supernova hit one edge before the other, giving it a nudge. Perhaps the magnetic fields threading through the gas created a subtle twist. Whatever the cause, or more likely the combination of causes, the cloud inherited a net rotation. Not much, just a tiny drift in one direction. But it was enough. Scientists have calculated that even a rotation speed of just a few meters per second across the original cloud would be sufficient. Over millions of years, as the cloud collapsed and conserved its angular momentum, that slow drift would become a vigorous spin. And once the spin started accelerating, there was no stopping it. Here's where things get interesting. As the cloud collapsed, it didn't collapse uniformly. Remember, it was spinning, and that spin created an outward force at the equator, centrifugal force. This force opposed gravity in one direction, preventing the cloud from collapsing into a sphere. Instead, the cloud flattened. It became a disk. Imagine wringing out a wet towel. When you twist it, the water doesn't stay evenly distributed. It concentrates in certain areas and spreads out in others. The same principle applies here, but with gas and dust instead of water and gravity instead of your hands. The material falling toward the center of the cloud couldn't fall straight in. The rotation deflected it, forcing it to spiral inward like water circling a drain. And as it spiraled, it spread out into a flat plane, the path of least resistance. This is called an accretion disk, and it's one of the most common structures in the universe. Planets form from accretion disks around young stars. Stars form from accretion disks in nebulae. Even supermassive black holes have accretion disks of superheated gas spiraling into them. The disk is nature's way of conserving angular momentum while allowing matter to move inward. Now here's something that surprises many people. The direction of the spin was essentially random, or rather, it was determined by the specific conditions of the cloud's environment billions of years ago. There was no cosmic law that said it had to spin one way or the other. If the initial motions within the cloud had been slightly different, if that supernova shockwave had come from a different angle, or if a nearby star had passed on the other side, the cloud might have spun in the opposite direction. And if it had, our planets today would orbit the sun in the opposite direction. But once the direction was set, it was locked in. Every particle of gas, every grain of dust, every atom in the collapsing cloud inherited that same sense of rotation. Counterclockwise when viewed from above the north pole of the eventual solar system. This is why all the planets orbit the sun in the same direction today. They're not following each other. They're following the original spin of the cloud. A spin that was set in motion 4.5 billion years ago by a combination of gravitational tugs, magnetic fields, and shock waves whose sources have long since vanished. It's a kind of cosmic inertia. Motion, once begun, perpetuated forever. Let's think about this more carefully. Angular momentum isn't just conserved in the total system. It's conserved locally too. That means each part of the cloud, as it collapsed, carried its own piece of the spin with it. Imagine the cloud as a vast collection of particles, each one on its own trajectory. Some near the center, moving quickly. Some far out, moving slowly. But all of them moving in the same general direction around the axis of rotation. As these particles collided, they didn't cancel each other out. Instead, they averaged their motions. Particles moving slightly faster slowed down a bit. Particles moving slightly slower sped up a bit. Over time, through countless collisions, the motion became more uniform, more organized. This process is called collisional damping, and it's crucial to understanding how disks form. The turbulence we talked about earlier, the chaotic swirls and eddies, gradually got smoothed out as particles collided and exchanged momentum. What was once messy became orderly, but the overall direction of spin never changed. It couldn't. That information was baked into the system from the start. There's a beautiful irony here. The chaos of the early cloud, the turbulence, the asymmetries, the random collisions is what gave it angular momentum in the first place. But that same chaos through collisions and interactions gradually organized itself into a smooth, rotating disk. Order from disorder. Structure from randomness. It's one of the universe's recurring themes. Now let's talk about what was happening to different parts of the cloud as it spun and collapsed. Near the center where gravity was strongest, material fell inward fastest. The density increased. Particles collided more frequently. The temperature began to rise, not from any external heat source, but from the compression itself. When you compress gas, it heats up. It's the same reason a bicycle pump gets warm when you use it. This central region would eventually become the sun. But we're not there yet. At this stage, it was just a denser, warmer clump at the heart of the disk, what astronomers call a protostellar core. Farther out in the disk itself, the material was cooler, thinner, more spread out. The particles here weren't falling straight toward the center. They were in stable orbits circling the core, held in balance between gravity, pulling inward, and centrifugal force pushing outward. This is where the planets would eventually form. But again, not yet. Right now, it was just gas and dust orbiting in circles, colliding gently, sticking together in tiny clumps. And here's the key. Every particle in the disk was moving in the same direction. The same sense of rotation, counterclockwise from above. Because they all inherited that motion from the original cloud. There were no particles moving backward, no rogue dust grains orbiting the wrong way. The angular momentum of the system had been distributed throughout the disk, and every part of it followed the same rotational pattern. This uniformity of motion is why planet formation was even possible. If particles had been moving in random directions, collisions would have been destructive. They would have shattered each other into smaller pieces rather than sticking together. But because they were all moving in roughly the same direction, collisions were gentle, more like docking than crashing. Think of it like merging onto a highway. If all the cars are moving in the same direction at similar speeds, merging is smooth. But if cars were moving in opposite directions or at wildly different speeds, chaos would ensue. The disk was a highway, and every particle was moving in the same lane at roughly the same speed in the same direction. Let's consider a question. You might have been wondering, how long did all of this take? The initial collapse of the cloud from a diffuse nebula to a flattened disk with a dense core took somewhere between 100,000 and 1 million years. That might sound like a long time, but in cosmic terms, it's incredibly fast. Blink, and you'd miss it. The spin itself accelerated gradually over this period. At first, the cloud's rotation was barely noticeable, perhaps one full rotation every few million years. But as it collapsed, that rotation sped up dramatically. By the time the disk had fully formed, it might have been completing a rotation every few thousand years near its outer edges and every few years near the center. Today, the sun rotates once every 25 days at its equator. The planets orbit much more slowly. Earth takes 365 days, Jupiter takes 12 years, Neptune takes 165 years. But they're all still spinning in the same direction, following the pattern set by that ancient cloud. Angular momentum, once established, doesn't fade. It persists. Here's a thought worth sitting with for a moment. Every motion in the universe has a history. Nothing spins without a reason. Nothing orbits without a cause. And yet, the causes are often so far removed in time and space that they seem almost invisible. The reason our planets move the same way is because a cloud moved a certain way 4.5 billion years ago. And that cloud moved that way because of events even older: supernova explosions, galactic dynamics, magnetic field interactions, stretching back through time like an infinite chain of causes and effects. We are living inside the consequences of motions set in place before the Earth existed, before the Sun existed, before anything in our solar system was more than a whisper in the dark. And yet we feel it every day, every sunrise, every season, every year. The motion never stops. It never even slows down significantly. It just continues carrying us with it through space and time. Some people find that unsettling, the idea that we're on a planet spinning through space at incredible speeds with no way to stop, no way to get off. But there's comfort in it too, a kind of stability in the motion itself. We're not falling, we're orbiting. And that orbit, that motion, is the legacy of something far older and far grander than any of us. The cloud gave us more than just direction. It gave us stability. It gave us time. Time for the sun to ignite. Time for planets to form. Time for life to begin. Time for a species to evolve that could one day look up at the night sky and ask, why does everything move the same way? And the answer written in the spin of atoms and the dance of dust is this: because once long ago, something began to turn, and it never stopped. But the spin alone wasn't enough. Spinning creates order, yes, but it doesn't create structure. For that, something else had to happen, something more violent, more transformative. The disk had to collapse further. The center had to ignite. And from that ignition would come light heat and the birth of a star that would hold everything together. The disk was spinning, organized, moving in unison, but it was still just a disk, flat, thin, spread across billions of kilometers, and at its heart, something was stirring, a density, a weight, a pull that grew stronger with every passing millennium. Gravity doesn't ask permission. It doesn't wait. Once it starts pulling, it doesn't stop until something pushes back. And for a long time, nothing pushed back hard enough. So the collapse continued, deeper, faster, more inevitable. The cloud that had once been diffuse and scattered was now concentrating its mass, drawing itself inward, becoming something more focused, more powerful, more alive. This is the moment when potential became kinetic, when structure began to solidify, when the solar system stopped being an idea and started becoming real. Let's return to the disk. We left it spinning, flattened, with a dense core forming at its center. But dense is a relative term. Even at this stage, the core was still far less dense than the air you're breathing right now. Space is by nature empty. Even when it's full, it's mostly void. But emptiness can be deceptive, because in that void, there were particles, countless trillions upon trillions of them, and each particle had mass, and mass attracts mass. Gravity is the great gatherer. It reaches across distances, invisible and patient, pulling everything toward everything else. The more mass gathered in one place, the stronger the pull became. And the stronger the pull, the more mass it could gather. It's a feedback loop, a self-reinforcing cycle. Scientists call it gravitational instability, and it's one of the fundamental processes in the universe. Once it starts, it accelerates on its own. In the center of our disk, this process was well underway. The protostellar core, still not a star, not yet, was growing heavier by the second. Not literally by the second, of course. In reality, it took thousands of years for noticeable changes to occur. But on cosmic timescales, that's remarkably fast. Material from the surrounding disk spiraled inward, pulled by the core's gravity. But it couldn't fall straight in. Remember, everything in the disk was already in motion, orbiting the center. To fall inward, it had to lose angular momentum, shed some of its rotational energy. How does orbiting material lose angular momentum? Through friction. In the disk, particles collided with each other constantly. Gas atoms bumped into dust grains. Dust grains bumped into other dust grains. These collisions weren't violent. Most were gentle, almost imperceptible. But each collision transferred a tiny bit of energy, a tiny bit of momentum. Over time, through countless billions of collisions, the material in the disk gradually spiraled inward. Slowly, steadily, like water circling a drain getting closer and closer to the center. And as material fell inward, something crucial happened. It heated up. This might seem counterintuitive. After all, the disk started out cold, close to absolute zero. Why would it get hotter as it collapsed? The answer lies in a fundamental principle of physics. When you compress gas, you add energy to it. That energy has to go somewhere, and it goes into heat. Think of a bicycle pump. When you push the plunger down, compressing the air inside, the pump gets warm. You can feel it. The air molecules squeezed into a smaller space move faster. Faster motion means higher temperature. The same thing happened in the collapsing disk, but on an unimaginable scale. Near the center, where the compression was strongest, the temperature began to rise dramatically. Not all at once, this was a gradual process, taking tens of thousands of years, but gradually, the core went from being barely warmer than the surrounding space to being noticeably hotter. Tens of degrees, then hundreds, then thousands. At a few thousand degrees Kelvin, something important happened. The dust grains began to evaporate. Remember, these dust grains were made of materials like silicates, metals, and ices. They could only exist in solid form at low temperatures. As the core heated up, the ices evaporated, first water, methane, ammonia, turning back into gas. Then the more heat-resistant materials began to break down. Eventually, even rocky silicates and metals started to vaporize. The core became a cauldron of gas. Dense, hot, turbulent gas. No longer a solid thing you could touch, but a roiling mass of atoms colliding at incredible speeds. And still, gravity pulled inward. Still more material fell from the disk into the core. The mass increased. The temperature increased. The pressure increased. Pressure is another key player in this story. As more and more gas piled into the core, the weight of the outer layers pressed down on the inner layers. Deep inside, near the very center, the pressure became immense, millions of times greater than the atmospheric pressure on Earth's surface. At those pressures, matter behaves differently. Atoms are squeezed closer together than they'd ever be under normal conditions. Electrons are stripped away from nuclei. The gas becomes ionized, a plasma like the interior of a lightning bolt, but far more dense and far hotter. This is the state of matter inside stars, and the core was on its way to becoming one. But it wasn't there yet. The temperature, though rising, was still too low for the most important reaction of all nuclear fusion. For hydrogen atoms to fuse into helium, the process that powers stars, the temperature needs to reach about 10 million degrees Kelvin. The core was hot, yes, but it was still only tens of thousands of degrees. It had a long way to go. During this phase, the object at the center is called a protostar. Not yet a true star, but not just a clump of gas either. Something in between. A star in the process of being born. And here's where the story gets even more interesting. As the protostar grew, it began to emit radiation. Not visible light, not yet, but infrared radiation. Heat. The kind of glow you'd see with a thermal camera, not with your eyes. This radiation had an effect on the surrounding disk. It heated the inner regions, preventing them from collapsing further. It created a kind of standoff gravity, pulling inward radiation pressure, pushing outward. For a time, they balanced each other. But farther out in the disk, beyond the reach of the protostar's heat, the collapse continued. More material spiraled inward. The disk became more organized, more stratified. Different regions developed different characteristics. Close to the protostar, only the most heat-resistant materials survived. Metals, like iron and nickel. Refractory minerals, like aluminum oxide and calcium aluminum inclusions, some of the first solid materials to condense out of the hot gas. These would eventually become the building blocks of the inner rocky planets. Farther out, beyond what we now call the frost line, temperatures stayed low enough for ices to remain solid. Water, ice. Ammonia, ice. Methane, ice. This region was rich in material much more than the inner disk, because ice is abundant in the universe. Hydrogen and oxygen are common elements, and when they combine, they form water. This abundance of material in the outer disk is one reason why the outer planets, Jupiter, Saturn, Uranus, Neptune, became so much larger than the inner planets. There was simply more stuff to work with. But we're getting ahead of ourselves again. At this point, there were no planets yet. Just a disk stratified by temperature with material continuing to spiral inward toward the growing protostar at the center. Let's talk about the shape of this collapse. It's easy to imagine it as smooth uniform like water pouring into a funnel. But the reality was far more complex. The disk wasn't perfectly smooth. It had ripples, waves, spiral arms. As material moved inward, it didn't move in neat circular orbits. Gravitational interactions between different parts of the disk created instabilities regions where density increased, suddenly forming clumps and streamers. These instabilities are crucial. They're what allowed planets to eventually form. If the disk had been perfectly smooth material, might have just continued spiraling into the protostar, with nothing left over for planets. But the instabilities created pockets of concentrated material seeds that could grow into something larger. Scientists believe these spiral density waves in the disk acted like highways channeling material into specific regions. Where the waves converged, material piled up. Where they diverged, material thinned out. Over time, these pockets of concentrated material became the birthplaces of planets. But that's still in the future. Right now, the disk was just beginning to organize itself into distinct regions. There's a common misconception that the disk was calm, serene, like a still pond. People imagine it as a peaceful place quietly waiting for planets to form. But the truth is quite different. The disk was dynamic, turbulent, violent in its own slow way. Gas moved at speeds of kilometers per second. Particles collided constantly. Magnetic fields threaded through the plasma, creating currents and eddies. Shock waves from the protostar's activity rippled outward through the gas. And there was wind. Not wind in the sense we know it on Earth, but stellar wind. Streams of charged particles ejected from the protostar's surface. These winds were powerful, carrying away mass and angular momentum, shaping the disk, carving out cavities near the center. In fact, one of the mysteries scientists still grapple with is this. If angular momentum is conserved, how did so much material manage to fall into the protostar? The material in the disk was spinning, orbiting. To fall into the center, it had to get rid of its angular momentum somehow. The answer seems to involve a combination of factors. Magnetic fields played a role linking material in different parts of the disk and allowing angular momentum to be transferred outward even as mass moved inward. Turbulence in the disk created friction dissipating energy and allowing material to spiral inward. And the stellar winds carried away some angular momentum, helping to clear the path for infall. It's a delicate balance. Too much angular momentum, and the disk would never collapse. Too little, and everything would fall straight into the center, leaving nothing behind for planets. Somehow, our disk struck the right balance. Enough material fell inward to build a star. Enough stayed in the disk to build planets. And all of it kept spinning in the same direction, preserving the angular momentum of the original cloud. Let's pause for a moment and consider the timescales involved. The entire collapse phase from the initial flattening of the cloud to the formation of a protostar at the center took somewhere between 100,000 and 1 million years. That might sound like a long time, but consider this. The sun has been shining for 4.5 billion years. The collapse phase was less than 1,000th of the sun's current lifetime. If the sun's life were compressed into a single day, the collapse phase would last about 1 minute. A cosmic blink. And yet, in that blink, everything was decided. The mass of the sun, the structure of the disk, the distribution of material that would determine how many planets formed, and where and what they'd be made of. Fast, decisive, irreversible. One more thing worth mentioning. The disk wasn't isolated. It existed in a larger environment, a stellar nursery likely filled with other collapsing clouds, other protostars, other disks. These neighbors had effects on each other. Radiation from nearby massive stars could heat the outer edges of the disk, causing some material to evaporate and drift away. Gravitational interactions with passing stars could disturb the disk, stripping away some of its outer regions. Shock waves from nearby supernova explosions could compress the disk, triggering instabilities. Our solar system didn't form in a vacuum. It formed in a crowded, chaotic neighborhood. And that environment shaped its development in ways we're still trying to understand. But through all of this, the collapse, the heating, the turbulence, the external influences, one thing remained constant: the direction of rotation. Every particle in the disk, no matter how much it was jostled or heated or collided with others, kept moving in the same general direction. Counterclockwise as seen from above. That's the legacy of angular momentum conservation. Once set in motion, the spin persisted. It couldn't be undone. It could only be redistributed, shared among different parts of the system. And that's why billions of years later, all the planets still orbit the same way. They're following the path laid down by the collapsing disk. A path carved by gravity, shaped by spin, and preserved through time. Gravity pulled everything inward, yes, but spin kept it organized. Together, they created structure from chaos, order, from randomness. A disk that would become a solar system, a cloud that would become a sun, and planets, and moons, and eventually a place where life could ask questions about its own origins. But the protostar at the center wasn't finished yet. It was hot, yes, but not hot enough. Dense, yes, but not dense enough. The collapse had brought it close to the threshold, but one final push was needed. One final transformation that would change everything. That moment when the core finally reached the critical temperature and pressure, when hydrogen began to fuse into helium, when the protostar became a true star, was still to come. And when it came, it would flood the disk with light, carve out the inner solar system, and set the stage for everything that followed. Deep in the core beneath, layers upon layers of collapsing gas, something was about to cross a threshold, a point of no return. The temperature was climbing, the pressure was mounting, and at the very heart of what would become our sun, hydrogen atoms were being squeezed closer together than they had ever been before. For millions of years, the protostar had been almost there, almost hot enough, almost dense enough, but almost doesn't ignite a star. Then one moment, impossible to pinpoint, impossible to witness the conditions, became just right, and the universe's most fundamental energy source switched on, not with a bang, not with fanfare, just a quiet beginning, a single fusion reaction, then another, then billions more, every second, forever. The sun was born. Let's slow down and understand what actually happened in that moment, because it's one of the most profound transformations in nature, the moment when matter becomes energy, when gravity becomes light, when a collapsing cloud becomes a living star. At the core of the protostar, the temperature had been rising for hundreds of thousands of years. 10,000 degrees, 50,000, 100,000. But nuclear fusion requires something far more extreme. The nuclei of hydrogen atoms, single protons, need to be slammed together with such force that they overcome their natural repulsion and fuse into something heavier, helium. Protons are positively charged, and like charges repel. It's one of the fundamental rules of electromagnetism. To get two protons close enough to fuse, you have to overcome that repulsion, which requires incredible energy, incredible heat. Scientists estimate the threshold is around 10 million degrees Kelvin. At that temperature, the hydrogen nuclei are moving so fast, zipping around at hundreds of kilometers per second, that when they collide, they have enough energy to overcome the electromagnetic barrier and get close enough for the strong nuclear force to take over. The strong force is aptly named. It's one of the four fundamental forces of nature, and at very short ranges, distances smaller than an atomic nucleus, it's far stronger than electromagnetism. When two protons get close enough, the strong force grabs them and binds them together, releasing a tremendous amount of energy in the process. This is nuclear fusion, the process that powers every star in the universe, the process that has been lighting the sun for 4.5 billion years, the process that will continue for another 5 billion years or more. When the core of our protostar finally reached that critical temperature, 10 million degrees, fusion began, not everywhere at once, but in a small region at the very center where conditions were most extreme. A sphere perhaps only a few hundred kilometers across, tiny compared to the size of the protostar as a whole. But that tiny sphere began pumping out energy, vast, almost incomprehensible amounts of energy. Every second in the core of the sun, about 600 million tons of hydrogen are converted into helium. That might sound like a lot, and it is. But remember, the sun is enormous. It contains enough hydrogen to sustain this rate of fusion for billions of years. And here's the crucial part: when hydrogen fuses into helium, a tiny amount of mass is converted directly into energy. Einstein's famous equation E equals mc squared tells us exactly how much energy. The speed of light squared is a huge number, so even a tiny amount of mass produces a tremendous amount of energy. Every second, the sun converts about 4 million tons of matter into pure energy. That energy radiates outward from the core, traveling through the layers of the sun, eventually reaching the surface and streaming out into space as light and heat. Some of that light, 8 minutes later, reaches Earth, warms the atmosphere, powers photosynthesis, makes life possible. But we're getting ahead of ourselves. Let's stay in those early moments when fusion first ignited. The sudden release of energy had an immediate effect. It created pressure, lots of it. The outward pressure of radiation pushing against the inward pull of gravity. For the first time since the collapse began, something was pushing back against gravity with enough force to make a difference. And something remarkable happened. The collapse stopped. Not everywhere, not immediately. But in the core, where fusion was occurring, an equilibrium was reached. The outward pressure from fusion balanced the inward pull of gravity. The protostar stopped shrinking. It stabilized. This balance is called hydrostatic equilibrium, and it's what defines a true star. As long as fusion continues, the star maintains its size, neither collapsing further nor expanding. It's a delicate balance, and it can last for billions of years. Our sun reached that equilibrium about 4.5 billion years ago, and it's been in that state ever since, burning hydrogen, radiating energy, holding itself up against gravity's relentless pull. But here's something that surprises many people. The sun is not a ball of fire. It's a ball of plasma-ionized gas, where electrons have been stripped from their nuclei by the intense heat. There's no combustion happening, no chemical burning. Just nuclear fusion deep in the core, releasing energy that slowly makes its way to the surface. It takes a photon of light about 100,000 years to travel from the core of the sun to its surface. Not because the distance is vast. The sun's radius is only 700,000 kilometers, but because the interior is so dense that photons are constantly absorbed and re-emitted by atoms. They take a random walk, bouncing around, zigzagging through the plasma, gradually drifting outward. Eventually they reach the surface, escape into space, and 8 minutes later, some of them reach your eyes. Light from the core of the sun, born in fusion, aged 100,000 years, before it even left the star, finally arriving to warm your face. Now let's talk about what this newly ignited sun meant for the surrounding disk. When the sun turned on, it didn't just emit light. It emitted a powerful stellar wind streams of charged particles, protons, and electrons, blasting outward at hundreds of kilometers per second. This wind swept through the inner solar system, pushing on the gas in the disk, clearing out the lighter elements. This is one reason why the inner planets, Mercury, Venus, Earth, Mars, are made mostly of rock and metal. The sun's wind blew away most of the hydrogen and helium from the inner disk. Only the heavier elements, the materials that could resist being swept away, remained. Farther out beyond the frost line, the sun's influence was weaker. The wind didn't reach as strongly. The temperatures stayed low. The ices remained solid. And the gas hydrogen and helium stayed in place, allowing the giant planets to form with massive atmospheres. The sun didn't just light up the solar system, it shaped it, defined it, set the boundaries for what could exist, where. But here's something interesting. Even though the sun contains 99.86% of the total mass of the solar system, it contains only about 1% of the total angular momentum. Think about that. Almost all the mass, but almost none of the spin. The planets, moons, asteroids, and comets making up less than 1/5 of 1% of the solar system's mass carry 99% of its angular momentum. How did this happen? Remember, the original cloud was spinning. As it collapsed, angular momentum was conserved, but the way it was distributed changed dramatically. Most of the mass fell into the center and became the sun, but most of the angular momentum stayed in the disk carried by the material that would eventually become planets. This distribution was mediated by magnetic fields, by the transfer of momentum during the collapse, by the stellar wind carrying away some of the sun's rotational energy. The details are complex, and scientists are still working to fully understand the mechanisms. But the result is clear. The sun rotates slowly about once every 25 days at its equator, while the planets orbit much more slowly, but carry far more angular momentum. It's a curious inversion. The thing with the most mass has the least spin. The things with the least mass carry the most angular momentum. And yet, everything still moves in the same direction. The sun rotates counterclockwise, as seen from above the North Pole. The planets orbit counterclockwise. Most of the planets rotate counterclockwise on their axes, all following the same pattern inherited from the original cloud. Let's think about what the early sun looked like. It wasn't the calm, steady sphere we see today. Young stars are violent, unstable, prone to outbursts. The early sun went through a phase called the T Tauri phase, named after a star in the Taurus constellation that exhibits this behavior. T Tauri stars are young pre-main sequence stars that are still contracting toward their final size. They're characterized by strong stellar winds, intense magnetic activity, and dramatic flares, eruptions of energy that can briefly double the star's brightness. Our sun, in its infancy, was like this, flaring, blasting out radiation, hurling plasma into space. It was a tempestuous, energetic object, far more active than the sun we know today. These eruptions had profound effects on the disk. They heated the inner regions, vaporizing dust, driving chemical reactions, baking the material that would eventually form the rocky planets. Some scientists believe the intense radiation from the young sun may have melted and reformed the first solid materials in the inner solar system multiple times. There's evidence for this in meteorites. Some of the oldest meteorites we found contain tiny inclusions called CAIs, calcium aluminum rich inclusions. These are among the first solid materials to condense out of the solar nebula, and their chemical composition suggests they were heated to extremely high temperatures, melted, and resolidified. The young sun's fury left its mark on these ancient grains, a signature of violence preserved in stone, waiting 4.5 billion years for us to find and read. Over time, perhaps a few million years, the sun settled down. The fusion in its core stabilized. The outbursts became less frequent. the stellar wind calmed somewhat. The sun began its long, steady life as a main sequence star, but even as it stabilized, it continued to shape the system around it. The light and heat from the sun defined temperature zones in the disk, close in hot, farther out warm, beyond the frost line cold. Each zone favored the formation of different types of materials, different types of worlds. One more thing worth considering. The sun is remarkably stable compared to many other stars. It's not a variable star pulsing in brightness. It's not a binary system with a companion star disrupting the disk. It's not a massive star burning through its fuel in millions of years and exploding as a supernova. It's just a medium-sized, medium-temperature, medium-lived star, average in almost every way. And that averageness was crucial for what came next. If the sun had been much larger, it would have burned hotter and lived shorter. Planets might not have had time to form before the star died. If it had been much smaller, it might not have emitted enough heat to create the temperature zones necessary for diverse planet formation. But it was just right. Just massive enough to ignite fusion. Just stable enough to last billions of years. Just the right temperature to create a habitable zone, a region where liquid water could exist on a planet's surface. And it continues spinning slowly in the same direction it always has. The same direction the planets orbit. The same direction the original cloud rotated 4.5 billion years ago. Some people imagine the sun as stationary, with the planets moving around it. But that's not quite accurate. The sun is moving too. It wobbles slightly, tugged by the gravity of Jupiter and the other planets. It orbits the center of the Milky Way, completing one full trip every 230 million years. And it rotates on its axis once every 25 days, at the equator slightly slower near the poles. Everything moves. Everything spins. Nothing is truly still. The birth of the sun was the turning point. Before it ignited, the system was just a collapsing cloud following gravity's pull. After it ignited, the system had a center, a source of light and heat, a gravitational anchor, something that could hold everything else in place. And in the disk around that newborn star, something else was beginning to happen. The dust grains floating through the gas were starting to collide more frequently, starting to stick together, starting to grow. From those tiny collisions, larger structures would emerge: pebbles, boulders, planetesimals, protoplanets, and eventually worlds, rocky worlds close to the sun, giant worlds far from it, each one still orbiting in the same direction, following the ancient pattern, the memory of spin that began in a cloud long ago. With the sun burning at the center, the disk around it was no longer just a cloud of gas and dust. It had become something more structured, more purposeful. A workshop where the smallest particles would slowly, patiently build themselves into worlds. But how? How do microscopic grains of dust, each one smaller than a bacterium, become planets thousands of kilometers across? How does something so small become something so large? The answer lies in a process so gradual, so delicate, it seems almost impossible. And yet it happened. Grain by grain, collision by collision. Over millions of years, dust became pebbles, pebbles became boulders, boulders became mountains, and mountains became worlds. This is the dance of dust, the slow accumulation, the patient gathering, and every step of it happened while moving in the same direction, following the spin of the ancient cloud in the disk surrounding the newborn sun, the conditions were vastly different from what we'd left behind. The sun's light now illuminated the inner regions. Its heat warmed the gas. Its stellar wind pushed and shaped the material. The disk was no longer dark and cold. Everywhere at gradients, zones, regions with distinct characteristics. But despite these changes, one thing remained constant. Everything was still orbiting in the same direction. Counterclockwise as seen from above, the gas flowed in circular paths around the sun. The dust grains drifted along with the gas carried by its motion, sharing its direction. This uniformity of motion was essential for what came next, because the first step in building a planet is getting dust grains to stick together. And for that to happen, collisions need to be gentle. Imagine 2 grains of dust floating in space. Each one is about a micron across roughly 1/100th the width of a human hair. They're made of silicate minerals, or perhaps iron, or maybe coated with a thin layer of ice. And they're moving through the disk orbiting the sun along with trillions of other grains. Eventually, by chance, these 2 grains collide. What happens next depends on how fast they're moving relative to each other. If they're moving in completely different directions, one going clockwise, the other counterclockwise, for example, the collision would be violent. They'd smash into each other at high speed and shatter into smaller pieces. No growth, just destruction. But if they're moving in the same direction at similar speeds, the collision is gentle. A tap, not a crash. And when that happens, something remarkable occurs. They stick together. Scientists call this process coagulation, and it's the first step in planet formation. The forces that hold the grains together are weak van der Waals, forces electrostatic attraction, sometimes the stickiness of ice. But they're enough. 2 grains become one slightly larger particle. Then that particle collides with another grain, and they stick. Now there are 3 grains together, then 4, then 10, then hundreds. This process continues slowly, gradually, over thousands of years. The particles grow from microns to millimeters, from grains of dust to grains of sand. But here's where it gets tricky. There's a size range roughly from millimeters to meters where things become difficult. Scientists call this the meter-size barrier, and it's one of the biggest puzzles in planet formation. The problem is this: as particles grow larger, they start to interact more strongly with the gas in the disk. And the gas isn't orbiting at quite the same speed as the particles. There's a slight difference, a headwind essentially, that creates drag. For small dust grains, this drag is negligible. But for meter-sized objects, it becomes significant. The drag slows them down, and when they slow down, they lose altitude. They begin to spiral inward toward the sun, and they spiral inward fast. Scientists calculate that a meter-sized boulder in the inner solar system would spiral into the sun in less than 100 years. That's not nearly enough time for it to grow into something larger. So, how did anything survive this barrier? How did particles grow past this dangerous size range? The answer seems to involve several mechanisms, and scientists are still debating which ones were most important. One possibility is called gravitational instability. If the disk was dense enough in certain regions, the dust could clump together, directly bypassing the slow, grain-by-grain growth. These clumps, held together by their own weak gravity, could quickly become large enough to resist the drag. Another possibility involves turbulence in the disk. Eddies and vortices in the gas could trap particles, concentrating them in specific regions. In these concentration zones, particles would collide more frequently, growing faster, perhaps fast enough to leap over the meter-size barrier. A third mechanism is called streaming instability. It's a complex process involving the interaction between dust and gas, where concentrations of particles create localized pressure differences that cause even more particles to collect in the same spot. This positive feedback loop can rapidly produce large clumps. Whatever the exact mechanism, and it was probably a combination of all of these, somehow some particles made it through. They grew past the meter-size barrier and became larger objects, tens or hundreds of meters across. Objects large enough that their own gravity started to matter. These objects are called planetesimals. Not quite planets, but the building blocks of planets. Rocky bodies irregularly shaped, ranging from the size of a house to the size of a mountain, and once they formed, a new process took over: gravitational accretion. Planetesimals had enough mass to attract other objects with their gravity. When two planetesimals got close enough, gravity pulled them together. Sometimes they merged smoothly, like two drops of water combining. Sometimes they collided violently, shattering into fragments that would later reaccrete. But either way, they grew. Larger planetesimals attracted more material, growing even larger. This is called runaway growth, and it's remarkably efficient. Over the course of perhaps 100,000 years, some planetesimals grew to hundreds of kilometers across. These larger bodies are called protoplanets. Not full planets yet, but getting closer. Objects large enough to start shaping their own surroundings, to clear out nearby material, to dominate their orbital zones. And here's the crucial point throughout all of this. From dust grains to planetesimals to protoplanets, everything kept moving in the same direction. The direction of the original disk, the direction of the cloud's spin. Why? Because angular momentum is conserved. Each collision transferred momentum, but the average motion remained the same. Particles moving counterclockwise collided with other particles moving counterclockwise, and the result was still counterclockwise motion. There was no mechanism to reverse the spin, no force to change the direction. The pattern was locked in from the beginning. Let's think about the timescales involved. From the initial sticking of dust grains to the formation of planetesimals took perhaps 100,000 to 1 million years. From planetesimals to protoplanets took another few 100,000 years. These might sound like long timescales, but remember, we're building planets, structures thousands of kilometers across, containing more mass than 1 trillion tons. Doing that in less than 1 million years is remarkably fast. One of the fascinating aspects of this process is that it happened differently in different parts of the disk. Close to the sun, inside the frost line, only rocky and metallic materials could survive. The protoplanets that formed here were relatively small, perhaps a few thousand kilometers across at most. These would eventually become Mercury, Venus, Earth, and Mars. Beyond the frost line, where temperatures stayed below the freezing point of water ice, was abundant. And ice is common in the universe. Hydrogen and oxygen are among the most abundant elements, and they combine easily to form water. With ice included, there was much more material available to build planets. The protoplanets that formed in the outer solar system grew much larger. Jupiter's core, for example, may have reached 10 Earth masses or more, while still in its protoplanet stage. That massive core then had enough gravity to capture huge amounts of gas, hydrogen, and helium from the surrounding disk, eventually becoming the giant planet we see today. But Jupiter and the other gas giants didn't just form and stay put. They interacted with the disk with each other and with the countless smaller bodies around them. These interactions caused them to migrate, to change their orbital distances over time. Some scientists believe Jupiter may have formed farther out and then migrated inward before settling into its current orbit. Others think it formed roughly where it is now. The details are still debated, but one thing is certain: the formation of the giant planets had profound effects on the rest of the solar system. Jupiter's gravity stirred up the asteroid belt, preventing a planet from forming there. It deflected comets, sending some into the inner solar system and flinging others out into interstellar space. It may have protected Earth from frequent asteroid impacts, acting as a gravitational shield. Or it may have caused more impacts by perturbing objects into Earth-crossing orbits. The jury is still out. But through all of this chaos, through all these interactions and migrations and collisions, one thing remained true. Everything orbited in the same direction. Jupiter-Saturn, Uranus-Neptune, all moving counterclockwise around the Sun, all inheriting the motion of the disk they formed from. Let's talk about the role of collisions in more detail, because planet formation wasn't just a gentle accumulation of dust. It was violent, especially in the late stages. Once protoplanets reached a certain size, perhaps a few hundred to 1,000 kilometers across, their collisions became truly catastrophic. These were no longer gentle taps. They were impacts that released more energy than all the nuclear weapons on Earth combined. Impacts that melted rock, vaporized atmospheres, excavated craters hundreds of kilometers wide. Scientists call this phase the late heavy bombardment, though that term is sometimes reserved for a specific period about 4 billion years ago, when the inner solar system experienced a spike in impacts. But really, the entire era of planet formation was heavy bombardment. It lasted tens of millions of years. Earth in its early days was struck by countless large objects. One impact was so massive, it's thought to have ejected a huge amount of material into orbit material that eventually coalesced into the Moon. That impactor, sometimes called Theia, may have been roughly the size of Mars. The collision melted Earth's surface, turned it into a magma ocean, and tilted Earth's axis to the 23.5-degree angle we see today. But even after that catastrophic event, Earth continued orbiting the Sun in the same direction. The impact didn't reverse its orbit. It couldn't. The angular momentum was too great, too deeply ingrained in the system. Here's something worth pondering. Every collision, every merger, every accretion event was random in some ways, which objects collided when with what energy. And yet the outcome was orderly. The planets ended up in roughly circular orbits, mostly in the same plane, all moving in the same direction. How did order emerge from chaos? The answer lies in the underlying structure of the disk. The disk itself was orderly flat, spinning in one direction, and everything that formed within it inherited that order. The randomness of individual collisions averaged out over millions of events. What remained was the pattern, the structure, the spin. It's a bit like shuffling a deck of cards. Each shuffle is random. But if you keep shuffling long enough, certain statistical patterns emerge. In the same way, the random collisions of planetesimals and protoplanets, repeated billions of times, produced a structured outcome, a solar system with planets in stable orbits, all moving the same way. One common misconception is that the planets formed at their current distances and have stayed there ever since. But the truth is more dynamic. Planets migrated. The disk exerted torques on them, changing their orbits. Gravitational interactions with each other caused resonances where their orbital periods became locked in simple ratios like Jupiter and Saturn, whose periods are in a 5:2 ratio. These migrations and interactions were complex, chaotic even. But through it all, the fundamental direction of motion remained unchanged. Counterclockwise. Always counterclockwise. Another misconception is that planet formation is finished. It's not. Even today, 4.5 billion years later, planets are still accreting material. Earth gains about 40,000 tons of mass every year from meteorites and dust falling from space. It's a tiny amount compared to Earth's total mass, but it's still happening. The process continues, just much more slowly than before. And here's something beautiful. We can see planet formation happening right now in other star systems. Telescopes like ALMA have imaged protoplanetary disks around young stars. And in many of them we can see gaps, dark rings, where planets are forming, sweeping up material in their orbital paths. In one famous image of a star called HL Tauri, we can see multiple concentric gaps, each one likely corresponding to a forming planet. The disk is spinning. The gaps are orderly concentric, all following the same direction of rotation. It's like looking at a photograph of our own past. 4.5 billion years ago, our solar system looked like that, a spinning disk with gaps where planets were growing, all moving in unison, all following the pattern set by the collapsing cloud. The dance of dust wasn't random. It was choreographed by gravity, guided by angular momentum, shaped by the structure of the disk. From the smallest grains to the largest planets, everything followed the same steps, moved to the same rhythm, spun in the same direction. And that's why, when you look up at the night sky and watch a planet drift slowly across the ecliptic Venus, in the evening Jupiter, at midnight Saturn, in the pre-dawn, you're seeing the continuation of a dance that began 4.5 billion years ago. A dance that started with dust, guided by spin, and created worlds. But not everything in the solar system follows the pattern perfectly. There are exceptions, anomalies, worlds that spin the wrong way or at strange angles or in orbits that seem out of place. And those exceptions tell their own stories, stories of violence, of accidents, of the chaos that still lurks beneath the order. The pattern seemed perfect, everything spinning in the same direction, all the planets orbiting counterclockwise, a solar system moving in harmony like a well-conducted symphony. But look closer and you'll find discordant notes, planets that spin backward, worlds tilted so far they're practically lying on their sides, moons orbiting the wrong way. These aren't mistakes. They're scars, evidence of violence, proof that even in the orderly solar system we see today chaos once ruled, and in some places, chaos won. So what happened? Why do some worlds refuse to follow the pattern? And what can these exceptions teach us about the hidden violence in our solar system's past? Let's start with the most famous exception, Venus, the second planet from the Sun. Earth's near twin in size and mass, and yet utterly strange in one crucial way. Venus rotates backward, while every other major planet in the solar system spins counterclockwise, following the original rotation of the solar nebula. Venus spins clockwise. Astronomers call this retrograde rotation. If you could stand on Venus's cloud tops and watch the sun, it would rise in the west and set in the east, the opposite of everywhere else. But here's the truly bizarre part. Venus rotates incredibly slowly. One rotation takes 243 Earth days. That's longer than Venus's year, which is only 225 days. So, on Venus, a day is longer than a year. Think about that for a moment. The planet completes an entire orbit around the sun before it completes a single rotation on its axis. Why? What could cause such strange behavior? The most widely accepted explanation is a catastrophic collision. Early in the solar system's history, perhaps during the chaotic late bombardment phase, Venus was struck by a massive object. Not a small asteroid, but something planet-sized. An impact so violent, it fundamentally altered Venus's spin. Computer simulations suggest that if a protoplanet roughly the size of Earth struck Venus at the right angle, it could have flipped Venus's rotation axis by more than 180 degrees. The planet would have been knocked upside down, essentially reversing its spin direction. But there's more to the story. That kind of collision would have been apocalyptic. It would have melted Venus's entire surface, vaporized oceans, if any existed, created a global magma sea that took millions of years to cool. The Venus we see today, with its thick carbon dioxide atmosphere, crushing surface pressure, and runaway greenhouse effect, may be the long-term consequence of that ancient violence. Some scientists propose an alternative explanation. Perhaps Venus's rotation was slowed down gradually by tidal interactions with its dense atmosphere and the sun's gravity. Over billions of years, this slowing could have eventually reversed the planet's spin. But most researchers find the impact hypothesis more convincing. The reversal is too complete, too dramatic to have been a slow process. Either way, Venus stands as a testament to the fact that the pattern we've been tracing, the uniform counterclockwise motion inherited from the solar nebula, can be broken. Angular momentum can be redirected. The past can be violently rewritten. Now, let's travel outward to another strange world, Uranus, the seventh planet from the Sun. A pale blue-green ice giant that, like Venus, doesn't follow the rules. Uranus is tilted. Not just a little, almost 98 degrees. Its rotation axis is nearly parallel to the plane of its orbit. While other planets spin roughly upright like tops, Uranus rolls along its orbit like a barrel. This means Uranus experiences the most extreme seasons in the solar system. Each pole gets 42 years of continuous sunlight, followed by 42 years of complete darkness. If you lived on Uranus's surface, assuming such a thing were possible, you'd experience a summer lasting decades, then a winter lasting just as long. The tilt is so extreme that Uranus's north pole currently points almost directly at the sun for part of its orbit. Imagine Earth tilted that way. The North Pole would become the equator, and the equator would become the pole. the entire climate system would be unrecognizable. What happened to Uranus? Again, the leading explanation is a massive collision. Scientists believe that during its formation, Uranus was struck by an Earth-sized protoplanet, or perhaps two smaller objects in succession. The impact knocked the planet onto its side, tilting its axis by nearly 90 degrees. But here's what's remarkable. Despite this catastrophic tilt, Uranus still orbits the Sun in the same direction as all the other planets, counterclockwise. The collision changed how the planet rotates, but it didn't change the planet's orbital motion, that deeper pattern. The orbital angular momentum inherited from the disk was too great to be disrupted by a single impact. It's like spinning a top and then hitting it from the side. You can make it wobble, even knock it over, but it keeps spinning in the same spot, following the same circular path. Uranus's moons are also tilted, orbiting in the planet's equatorial plane, which means they orbit almost perpendicular to the planet's orbital plane. They followed Uranus into its new orientation, loyal to their parent planet, rather than to the solar system's overall pattern. One more strange thing about Uranus, its magnetic field, is tilted 60 degrees from its rotation axis and doesn't pass through the planet's center. It's offset, skewed, as if the planet's interior is still settling from some ancient disruption. Perhaps another consequence of that long-ago collision, a wound that never fully healed. Let's look at one more major exception, Neptune's moon, Triton. It's the 7th largest moon in the solar system, roughly 3/4 the size of our own moon, and it orbits Neptune in the wrong direction. While Neptune rotates counterclockwise, and most of its moons orbit counterclockwise, Triton orbits clockwise, retrograde. It's moving against the flow, swimming upstream against the pattern established billions of years ago. This is profoundly strange. Moons almost always orbit in the same direction their planet rotates. They form from the disk of material surrounding the planet during its formation, and that disk shares the planet's rotational direction. A retrograde orbit suggests Triton wasn't born around Neptune at all. Scientists are now quite certain that Triton is a captured object. It formed somewhere else, probably in the Kuiper Belt, the region beyond Neptune, where icy bodies like Pluto reside. Triton may have originally been a dwarf planet in its own right, orbiting the Sun independently. But at some point, perhaps 3 to 4 billion years ago, Triton passed too close to Neptune. The giant planet's gravity captured it, pulling it into orbit. The process would have been chaotic. Triton might have had a highly elliptical orbit, initially swinging far from Neptune and then plunging close. Over time, tidal interactions with Neptune circularized the orbit, bringing Triton into the stable, nearly circular path it follows today. But those tidal interactions came at a cost. The friction generated enormous heat inside Triton, melting its interior, resurfacing the moon through cryovolcanism. Geysers of liquid nitrogen and water erupting from below. Today, Triton is one of the most geologically active moons in the solar system, despite being so far from the Sun's warmth. That activity is powered by the memory of its violent capture, and Triton's story isn't over, because its retrograde orbit means it's slowly spiraling inward toward Neptune. Tidal forces are stealing energy from its orbit, pulling it closer over time. In perhaps 3 to 4 billion years, Triton will cross the Roche, limit the distance at which Neptune's tidal forces will overcome Triton's own gravity and tear the moon apart. Triton will be shredded its material, spreading out to form a magnificent ring system around Neptune, far more spectacular than the faint rings that exist today. A captured world, doomed by its own capture. A moon moving against the pattern, paying the price for its defiance. These three examples, Venus, Uranus, and Triton, show us that the pattern of uniform rotation we've been exploring isn't absolute. It can be disrupted, violated, reversed. But here's what's crucial. It takes extraordinary violence to do so. A collision with a planet-sized object can flip Venus's spin, or knock Uranus on its side. A close gravitational encounter can capture Triton into a retrograde orbit. But these are rare events, catastrophes. And even when they happen, they don't disrupt the deeper pattern, the orbital motion around the Sun. Venus still orbits the Sun counterclockwise, even though it rotates clockwise. Uranus still orbits counterclockwise, even though it's tilted on its side. Triton orbits Neptune the wrong way, but Neptune itself orbits the Sun in the standard direction. The orbital angular momentum, the motion of planets around the Sun, is deeply entrenched. It's carried by objects with enormous mass moving at enormous speeds. To reverse a planet's orbit would require an impact far more energetic than anything that happened during the solar system's formation. It would probably destroy the planet entirely, rather than just reversing its motion. So the pattern persists even in the face of violence. The exceptions prove the rule by showing how hard it is to break. There are other oddities worth mentioning. Mercury has almost no axial tilt, just 2 degrees, meaning it has no real seasons. Its rotation is also strange. It completes 3 rotations for every 2 orbits around the Sun, locked in a 3-2 resonance by tidal interactions with the Sun. Mars has a tilt similar to Earth's, about 25 degrees, but it wobbles far more dramatically. Over millions of years, Mars's tilt can vary from near zero to as much as 60 degrees, causing wild swings in its climate. Earth is stabilized by the moon's gravitational influence, but Mars has no such large satellite to anchor it. And then there are the asteroids. Most of them tumble chaotically, their rotation axes pointing in seemingly random directions. But this makes sense. They're small, their gravity is weak, and they've been battered by billions of years of collisions. Each impact can change their spin. The smaller the object, the easier it is to alter its rotation. But the planets, massive distant from each other, relatively safe from further catastrophic collisions, have largely kept their orientations stable for billions of years. The exceptions are exceptions, precisely because they're rare. Here's a question worth considering. What would have happened if the collisions that affected Venus and Uranus had happened to Earth instead? If Earth had been flipped upside down, like Venus, our day length might be very different. Our magnetic field generated by Earth's rotation and the motion of liquid iron in its core might be altered. The climate patterns we know would be unrecognizable. If Earth had been knocked on its side like Uranus, the poles would receive decades of continuous sunlight or darkness. The temperature extremes would be far more severe than anything we experience now. Life, if it existed at all, would have evolved under very different conditions. We were lucky. Earth avoided the catastrophic collisions that struck other worlds. Or perhaps those collisions happened so early that the planet had time to recover before life began. Either way, we live on a world that mostly follows the pattern. A world whose spin still reflects the rotation of the ancient cloud. The exceptions, Venus, Uranus, Triton, and others, remind us that the solar system's history is not one of smooth, peaceful evolution. It's a history punctuated by violence, collisions, captures, disruptions. The orderly system we see today emerged from chaos, and the scars of that chaos are still visible if you know where to look. But even the scars follow patterns. Retrograde rotation requires a specific type of collision. Extreme axial tilt requires a specific impact angle. Captured moons require a specific set of gravitational circumstances. The exceptions aren't random. They're the result of physics, just like the rule itself. And here's something beautiful. By studying the exceptions, we learn more about the rule. By understanding how Venus got its backward spin, we understand better how planetary spins are normally established and maintained. By studying Uranus's tilt, we learn about the violence of the late bombardment period. By examining Triton's capture, we learn about the dynamics of the early outer solar system. The exceptions are data points. Each one tells a story. Each one is a chapter in the long, complex history of the solar system's formation. So, when you look up at Venus in the evening sky, remember that bright point of light is a world spinning backward, a planet that defied the pattern through violence. When you see Uranus through a telescope, if you're lucky enough to have one, remember that it's tilted on its side, rolling through space in a way no other major planet does. They're reminders that order is fragile, that the patterns we see in nature aren't inevitable. They emerged from specific conditions, and they persist only because those conditions allow them to. But persist, they do. Despite the exceptions, despite the violence, despite the chaos, the fundamental pattern remains. Most objects in the solar system orbit and rotate in the same direction, following the spin of the cloud that gave them birth. And now, with the exceptions acknowledged, with the scars examined, we can ask a deeper question. How do we know all of this? How can scientists looking at the solar system today reconstruct events that happened billions of years ago? What evidence remains of that ancient cloud, that collapsing disk, that violent birth? We've traveled 4.5 billion years into the past, watched a cloud collapse, seen a disk form, witnessed the birth of the sun and the slow accumulation of planets. But here's a question that might have been lingering in your mind. How do we know any of this actually happened? The cloud is gone. The disk dispersed long ago. We weren't there to watch. No telescope could have captured it. No spacecraft could have measured it. And yet scientists speak with confidence about events that occurred billions of years before humans existed. How? What evidence remains of that ancient beginning? What clues did the solar system leave behind, waiting to be discovered? The answer is everywhere. Written in stone, frozen in ice, spinning in orbits, glowing in distant star systems. The past isn't gone. It's preserved if you know how to read it. Let's start with the most direct evidence meteorites. Fragments of the early solar system that survived 4.5 billion years and eventually fell to Earth. They're not just rocks. They're time capsules. Messengers from the past carrying information about the conditions, temperatures, and processes of the primordial disk. Every year, thousands of meteorites land on Earth. Most burn up in the atmosphere, but some make it to the surface. And when scientists study these objects in laboratories cutting them open, analyzing their chemical composition under microscopes, they find something remarkable, clues to the solar system's birth. The most primitive meteorites are called chondrites. They contain tiny spherical structures called chondrules, millimeter-sized beads of rock that formed when molten droplets cooled rapidly in space. These chondrules are some of the oldest solid materials in the solar system, formed within the first few million years of the disk's existence. When scientists date these chondrules using radiometric techniques, measuring the decay of radioactive isotopes within them, they consistently get ages around 4.567 billion years. That's how we know when the solar system formed. Not from theory, but from direct measurement of ancient materials. But chondrites contain something even more intriguing: CAIs, or calcium aluminum rich inclusions. These are tiny white specks within the meteorite, often just a few millimeters across. And they're special because they formed at extremely high temperatures above 1,300 degrees Celsius. CAIs are thought to be the very first solid materials to condense out of the hot gas near the young sun. They formed in the innermost regions of the disk, where temperatures were highest, and somehow got mixed outward into the cooler regions, where the chondrite parent bodies were assembling. This mixing tells us something important. The early disk was turbulent. Material didn't just stay where it formed. It moved, circulated. Inner regions mixed with outer regions. And through all of that mixing, everything kept moving in the same general direction, preserving the overall pattern of rotation. Another type of meteorite, iron meteorites, tells a different story. These are fragments of the cores of small protoplanets that formed early in the solar system's history. These protoplanets grew large enough for their interiors to melt, allowing heavy metals like iron and nickel to sink to the center and form a metallic core. But something destroyed these protoplanets before they could grow into full-sized planets. Probably collisions, violent impacts that shattered them into fragments. The iron cores, now exposed, eventually broke apart into smaller pieces, some of which wandered through space for billions of years, before eventually crossing Earth's path. When scientists cut open iron meteorites, they find patterns called Widmanstätten, structures, beautiful geometric crystalline patterns that form only when molten metal cools incredibly slowly over millions of years. These patterns are proof that the parent bodies were once molten, differentiated worlds with cores and mantles just like Earth. But here's what's fascinating: the isotopic compositions of these meteorites. The ratios of different isotopes of elements like oxygen, titanium, and chromium vary slightly depending on where in the disk they formed. Inner solar system meteorites have different isotopic fingerprints than outer solar system meteorites. This variation tells us that the disk wasn't completely homogeneous. Different regions had slightly different compositions, probably because material from different parts of the original molecular cloud didn't mix perfectly. And yet, despite these variations, the overall structure was orderly. The disk was flat rotating, organized by temperature zones. Now, let's look beyond meteorites to the planets themselves. Their very existence, their arrangement, their properties, all of these provide evidence for the disk model. Consider the spacing of the planets. They're not randomly scattered. They follow a rough pattern, with each planet's orbital radius being roughly 1.5 to 2 times larger than the planet inside it. This isn't exact. It's not a perfect mathematical law, but it's close enough to suggest an underlying order. This spacing makes sense if planets formed from a rotating disk. In such a disk, material naturally organizes itself into concentric rings, each one dominated by the largest body in that region. The spacing reflects the gravitational influence each planet exerts on its neighbors, carving out a zone of cleared material around its orbit. And then there's the compositional gradient. The inner planets, Mercury, Venus, Earth, Mars, are rocky, made of metals and silicates. The outer planets, Jupiter, Saturn, Uranus, Neptune, are gaseous or icy, with thick atmospheres of hydrogen and helium. This isn't a coincidence. It's exactly what you'd expect from a temperature gradient in a protoplanetary disk. Close to the sun, only heat-resistant materials could condense. Rock, metal. Farther out beyond the frost line, ices could form. Water ice, ammonia, ice methane ice. Even farther out in the coldest regions, gases could be captured by massive cores. The planet's compositions are a map of the temperature zones in the ancient disk. One of the most compelling pieces of evidence comes from exoplanets, planets orbiting other stars. Since the discovery of the first exoplanet in the 1990s, astronomers have found thousands of planetary systems, and many of them show the same pattern: planets orbiting in the same plane, moving in the same direction, arranged in orderly systems. More importantly, we've directly observed protoplanetary disks around young stars. Telescopes like ALMA, the Atacama Large Millimeter Array, can peer through dust and gas to image these disks in stunning detail. One of the most famous images is of HL Tauri, a star system about 450 light-years away. When ALMA observed it, astronomers saw a nearly perfect disk of gas and dust, flat and circular, with multiple dark gaps carved out by forming planets. The disk was rotating, everything moving in the same direction, just like our solar system did 4.5 billion years ago. These observations are like looking at a photograph of our own past. We can't see our solar system as it was billions of years ago, but we can see other solar systems at that same stage of development right now. And they all show disks, rotating disks, flat disks, disks with gaps where planets are forming. The pattern repeats across the galaxy. It's not unique to us. It's the standard way solar systems form. Another form of evidence comes from computer simulations. Scientists can model the collapse of a molecular cloud, the formation of a disk, the growth of planetesimals, all using the laws of physics. They input the initial conditions of cloud with a certain mass, temperature, rotation rate, and composition, and let the simulation run. What do these simulations produce? Solar systems remarkably similar to our own. Planets forming in a disk, orbiting in the same direction, with rocky worlds close in and gas giants farther out. The simulations aren't perfect. They can't capture every detail, but they consistently reproduce the basic architecture of planetary systems. This is powerful evidence. It means the theory isn't just speculation. It's grounded in physics. The processes we've described, gravitational collapse, angular momentum, conservation, accretion, aren't just ideas. They're mathematical relationships that produce predictable outcomes, and those outcomes match what we observe. Let's talk about one more piece of evidence: the solar wind and the age of the sun itself. By studying the sun's spectrum, the specific wavelengths of light it emits, astronomers can determine its composition temperature and age. The sun is a main sequence star burning hydrogen into helium in its core, and models of stellar evolution tell us how long it's been doing that. The answer, about 4.6 billion years. The same age we get from meteorites. The same age we calculate for the formation of Earth and the other planets. Everything points to the same moment of origin, the same birth event. The sun also emits solar wind, a constant stream of charged particles flowing outward from its surface. When this wind reaches the edges of the solar system, it creates a boundary called the heliosphere. Spacecraft like Voyager 1 and Voyager 2 have crossed this boundary, entering interstellar space, and they've measured its properties. The structure of the heliosphere tells us about the sun's magnetic field, which is generated by its rotation. And that rotation, 25 days at the equator, slightly longer near the poles, is a remnant of the original angular momentum of the collapsing cloud. The sun is still spinning, the same way it began billions of years ago. Even the moon provides evidence. When scientists study moon rocks brought back by the Apollo missions, they find that the moon formed about 4.51 billion years ago, roughly 50 to 100 million years after the solar system itself. The prevailing theory is that the moon formed from debris ejected when a Mars-sized object collided with Earth. But here's the key: even after that collision, even after Earth was partially vaporized and the moon coalesced from the debris, Earth continued orbiting the sun in the same direction. The impact was catastrophic on a planetary scale, but it didn't reverse Earth's orbit. The angular momentum was too great, too deeply embedded in the system. One common misconception is that the story of the solar system's formation is just a theory, untested and unverifiable. But that's not true. It's a scientific theory, in the strongest sense of the word, a comprehensive explanation supported by multiple independent lines of evidence: meteorites, planetary compositions, exoplanet observations, computer simulations, stellar ages, all of them pointing to the same story. Another misconception is that we're just guessing about what happened billions of years ago. But we're not guessing. We're reading. Reading the evidence written in rocks and orbits, in light from distant stars. It's like archaeology, but instead of digging through layers of Earth, we're digging through layers of time, using physics and chemistry as our tools. Here's something that might surprise you. Scientists can even estimate the original mass of the protoplanetary disk by adding up the masses of all the planets, moons, asteroids, and comets, and accounting for the material that was ejected or fell into the sun. They estimate the disk originally contained about 1 to 3% of the sun's mass. That might not sound like much, but it's more than enough. 1% of the sun's mass is still 3,000 times the mass of Earth. Plenty of material to build 8 planets, hundreds of moons, and trillions of smaller objects. And here's another fascinating detail: the disk didn't last forever. Within about 10 million years, most of the gas in the disk was gone, blown away by the sun's stellar wind, accreted into planets, or dispersed into space. The window for forming gas giant planets, like Jupiter, was narrow. They had to grow quickly, capturing their massive atmospheres, before the gas disappeared We know this because we see young star systems where the disk is still present and others where it's already gone. By studying stars of different ages, astronomers can piece together the timeline of disk dispersal. It's like watching a time lapse of solar system formation spread across different star systems at different stages of development. One more piece of evidence deserves mention: comets. These icy bodies originating from the Kuiper Belt or the Oort cloud are leftovers from the outer solar system's formation. When they swing close to the sun and develop their characteristic tails, scientists can analyze the composition of the gas and dust they release. What do they find? Water ice, carbon dioxide ice, organic molecules, the same materials that would have been present in the outer regions of the protoplanetary disk, preserved in deep freeze for billions of years. Comets are samples of the original disk material, essentially unchanged since the solar system's birth. And when scientists measure the rotation of comet nuclei, they find, perhaps unsurprisingly, by now, that most of them rotate in the same general direction as the planet's orbit. Even these small, distant objects carry the memory of the disk's spin. Think about all of this evidence together: meteorites with precise ages, planetary arrangements that match disk models, direct observations of forming solar systems, computer simulations that reproduce the architecture we see, isotopic signatures that map the temperature gradient, comets carrying pristine samples of ancient ice. Each piece of evidence on its own is suggestive, but together they form an overwhelming case. The story we've been telling of a collapsing cloud, a rotating disk, a newborn sun, and slowly forming planets isn't speculation. It's reconstruction. A careful piecing together of clues left behind by events that happened long before we existed. It's humbling in a way to realize that rocks can remember what happened billions of years ago. That light from distant stars can show us our own past. That the orbits of planets are themselves a form of memory, preserving the motion of a cloud that no longer exists. Science doesn't require time travel to study the past. It requires patience, precision, and a willingness to listen to what the universe is telling us. And the universe has been telling us in countless ways how we came to be. So when you hold a meteorite, if you ever get the chance, remember that you're holding a piece of the solar system's childhood. When you look at Jupiter through a telescope, remember that its very existence is evidence of a disk that once surrounded a young sun. When you watch a comet streak across the sky, remember that it's a messenger from the distant past carrying news of how things began. The evidence is all around us, written in stone, spinning in orbits, shining in distant star systems, and all of it tells the same story over and over. Everything moves the same way, because everything came from the same spinning cloud 4.5 billion years ago. But understanding how we know the story is only part of the journey. There's one more question left to answer, one more layer to explore. Not about the past, but about the present, about what it means that we're still moving, still spinning, still following that ancient pattern, right now, in this moment. We've journeyed through 4.5 billion years, from a dark cloud floating in the Milky Way to the solar system we know today. We've watched dust become planets, chaos become order, and a random spin become a pattern that governs everything we see in the night sky. But here's the part that might take your breath away. It's still happening. Right now. This very moment. You're not reading about ancient history. You're living inside it. The motion that began in that primordial cloud hasn't stopped. It's carrying you right now through space at speeds almost too vast to comprehend. And it will continue long after you're gone, long after humanity is gone, perhaps until the sun itself dies. So let's come back to the present. Let's feel what it means to be part of this ancient dance. Right now, as you rest as these words drift through your mind, Earth is spinning beneath you. One full rotation, every 23 hours, 56 minutes, and 4 seconds. That's a sidereal day, the time it takes for Earth to rotate once relative to the distant stars. At the equator, this rotation carries you eastward at about 1,670 kilometers per hour, faster than the speed of sound. And yet, you feel nothing. No wind, no motion, because the atmosphere spins with you, because everything around you, the ground, the air, the buildings, the trees, is moving at the same speed. But the spin is real. If you could suddenly stop Earth's rotation, the atmosphere would continue moving eastward at over 1,000 kilometers per hour, creating winds that would scour the surface. Everything not anchored would be flung eastward by sheer momentum. It would be catastrophic. But Earth doesn't stop. It keeps spinning, counterclockwise as seen from above the North Pole. The same direction the solar nebula spun 4.5 billion years ago. And while Earth spins, it's also orbiting, moving around the sun at about 30 kilometers per second. That's 107,000 kilometers per hour. In the time it takes you to blink, Earth has traveled more than 3 kilometers through space. The orbit is nearly circular, but not quite. It's an ellipse, slightly elongated. Earth reaches its closest point to the sun, called perihelion, in early January. Its farthest point, aphelion, comes in early July. The difference is only about 5 million kilometers, or about 3% of the total distance. But even that small variation affects us. It's one of the subtle factors that influences Earth's climate, though not as much as the tilt of Earth's axis, which gives us our seasons. And here's something beautiful. Earth's orbit is stable. It doesn't spiral inward toward the sun. It doesn't drift outward into the cold. It maintains its distance year after year, century after century, eon after eon, held in place by the balance between the sun's gravity pulling inward and Earth's orbital momentum carrying it forward. This stability is a gift, a consequence of the orderly formation of the solar system. If planets had formed in chaotic orbits crossing each other's paths, colliding frequently, life would never have had the billions of years it needed to evolve. But they didn't. The planets formed in a disk, organized by angular momentum, separated by gravitational spacing. And that organization gave Earth the time and stability to become a living world. Now, zoom out further. The sun itself is moving. It orbits the center of the Milky Way, along with hundreds of billions of other stars. One complete orbit, a cosmic year, takes about 230 million Earth years. Since the sun formed, it has completed roughly 20 orbits around the galaxy. The sun's speed in this orbit, about 220 kilometers per second. That's nearly 800,000 kilometers per hour. fast enough to cross the distance from Earth to the Moon in less than 2 hours. And the direction of this galactic orbit, roughly counterclockwise when viewed from the Milky Way's north galactic pole. The pattern continues even at this vast scale. But there's more. The Milky Way itself is moving. It's part of a group of galaxies called the Local Group, which includes Andromeda and about 50 smaller galaxies. And the Local Group is falling toward a massive concentration of galaxies called the Virgo supercluster. At every scale, planet solar system, galaxy cluster motion. Everywhere motion. And much of it follows patterns established billions of years ago when structures first began to form in the early universe. We are passengers on a planet spinning through space, orbiting a star which orbits a galaxy, which moves through a universe that itself is expanding. And yet, from our perspective, everything feels still, calm, peaceful. That's the paradox of motion. When everything around you moves together, motion feels like stillness. You don't feel Earth's rotation because you're rotating with it. You don't feel Earth's orbit because you're orbiting with it. You're embedded in the motion carried along part of the flow. And that flow began with a cloud that started to spin and never stopped. Let's think about what this means on a human level. Every person who has ever lived, every birth, every death, every moment of joy or sorrow happened while Earth was spinning, orbiting following the pattern, set billions of years before the first human existed. Ancient civilizations looked up at the same stars, watched the same planets drift across the sky, witnessed the same moon rise and set. They didn't know about angular momentum or protoplanetary disks, but they saw the pattern. They saw that the sun rises in the east and sets in the west, that the moon waxes and wanes in a predictable cycle, that the planets move against the backdrop of stars, always along the same path, the ecliptic. They called this path the zodiac. They made stories about it, myths and legends to explain the patterns they saw. They were right to sense something profound in those patterns, even if they didn't understand the physics behind them. The patterns are older than humanity, older than life, older than Earth itself. They go back to the beginning, to the moment when a cloud began to collapse and a direction of spin was established. And here's something worth pondering. As you drift towards sleep, the motion will continue. Long after you're gone. Long after everyone you know is gone. Long after humanity itself, if we're not here forever. Earth will keep spinning. The sun will keep shining. The planets will keep orbiting. For billions of years, the solar system will continue much as it is today. Eventually, yes, things will change. The sun will exhaust its hydrogen fuel, swell into a red giant, and likely engulf Mercury and Venus. Earth, if it survives, will be scorched lifeless, a barren rock orbiting a dying star. The outer planets will drift in the cold as the sun fades to a white dwarf. But even then, even in that distant future, 5 billion years from now, the planets will still be orbiting in the same direction, counterclockwise, following the pattern that was set at the very beginning. Angular momentum doesn't fade. It doesn't wear out. It's conserved always until something actively takes it away. And in the emptiness of space, there's nothing to take it away. No friction, no resistance. Just endless motion perpetuated forever. In a way, the solar system is a kind of perpetual motion machine, not the impossible kind that violates the laws of thermodynamics, but a real one allowed by physics. Motion that continues indefinitely because there's nothing to stop it. It's a dance that began billions of years ago and will continue for billions of years more. And we're part of it. Right now. You and me. Everyone on Earth. Everyone who ever was or ever will be. Have you ever felt small looking up at the night sky? That's a natural feeling. We are small compared to planets and stars and galaxies. But we're also part of something vast, connected to it, made from it. Every atom in your body was forged in a star or in the Big Bang itself. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of it came from the same primordial materials that formed the solar nebula. You are made of stardust. Yes, but you're also part of the motion, part of the spin, part of the ancient pattern. When you feel Earth beneath your feet, you're feeling a planet that's spinning at over 1,000 kilometers per hour. When you watch the sun rise, you're watching the result of Earth's rotation, the same rotation inherited from a cloud 4.5 billion years ago. When you see the moon in the sky, you're seeing an object orbiting Earth in the same direction as everything else following the pattern. The universe is not random. It's structured, ordered by laws that play out over vast scales of time and space. And those laws, simple and elegant, created everything we see. Gravity, angular momentum, conservation of energy. These aren't just abstract concepts. They're the forces that shaped the solar system, that shaped Earth, that shaped the conditions for life to arise. And they're still at work, still shaping, still creating. Out in space right now, other clouds are collapsing, other disks are forming, other planets are being born. The process that created our solar system is happening elsewhere thousands of times over throughout the galaxy. We are not unique, but we are part of a pattern that repeats across the cosmos. And that's something worth feeling grateful for, isn't it? To live in a universe where order emerges from chaos, where complexity arises from simplicity, where a spinning cloud can become a system of worlds, one of which becomes a home for life, for consciousness, for minds that can look up and ask, why does everything move the same way? And the answer, as we've seen, is both simple and profound, because it all began with a spin that was preserved, amplified, distributed, but never lost. A spin that connects the smallest dust grain to the largest planet, the ancient past, to the distant future, the cloud that no longer exists to the solar system we see today. So as you rest, as sleep begins to find, you let yourself feel that motion, not with your body. You can't feel it directly, but with your mind. Imagine Earth turning slowly beneath you. Imagine the sun glowing at the center, holding everything in place. Imagine the planets distant and silent, following their paths through the dark. All of it moving. All of it spinning. All of it following the pattern laid down billions of years ago. You are part of an ancient dance, a cosmic ballet that began long before you existed and will continue long after you're gone. And there's something comforting. And that isn't there? Something peaceful. To know that you're not separate from the universe, but woven into it. That your existence, brief as it is, happens within a framework of motion and time that stretches far beyond human comprehension. The cloud is gone, the disk dispersed, but the motion remains. And you right now are riding that motion, spinning through space on a blue planet, orbiting a yellow star, following a path carved by gravity and spin. Everything still spins. Slowly. Steadily. Forever. And maybe that's the most beautiful part of the story. Not that it happened once long ago, but that it's still happening. Still unfolding. Still carrying us forward into whatever comes next. We've drifted through billions of years together, through clouds and disks, through collisions and births, through order and chaos, through the creation of worlds. We've seen how a simple spin became a pattern that governs everything we see in the sky. And we've learned that the reason all planets move in the same direction is not because they were designed that way, but because they all came from the same spinning cloud. Because angular momentum, once established, is conserved. Because the universe follows laws that create structure from simplicity. It's a story written in motion, in orbits and rotations, in the paths of planets and the spin of stars. And it's a story that includes you right now, in this moment. Thank you for drifting with me through this quiet journey, for listening to the story of how motion began and how it continues, for letting these words carry you through time and space. If you found peace in this journey, if you felt connected to something larger, remember, the next story is waiting. There are more questions to ask, more mysteries to explore, more quiet journeys through the cosmos. For now, though, rest. Let the motion carry you. Let the spin of an ancient cloud, preserved across billions of years, lull you into dreams. Sleep well. Dream gently. And know that you're part of something vast and beautiful and endlessly turning. Good night.